Thank you, Jerry. And once again, thank you, New Era Software, for sponsoring the zExchange and all of the education that you make available through the zExchange, and especially for these crypto sessions that we've been doing for now a little bit over a year. Now, this month, February, we're going to kind of throw you a little bit of a curve. In December, we had talked about the plan to go back and revisit some of the crypto basics topics. So we did the intro to crypto in January, and originally we were going to do the hardware, cover the hardware basics this month and next month, and then come back with sessions on ICSF. However, with the announcement of the Z13 by IBM in January, it's kind of changed our thinking a little bit. And I think there's enough technology, enough new crypto technology available on the Z13 that probably warrants a session just on the Z13. And hopefully that's what we're going to do in March. We've got to wait for the documentation to become available, and that won't happen until the Z13 GAs in early March. So hopefully in March we'll put together a session just on the Z13 and some of the new technology that's there. And then in April and May, we'll come back and do kind of the crypto hardware basics, followed by the ICSF basics. So with that, we had to come up with a topic for February, a new topic, and we settled on the encryption facility for ZOS. Last year, we had to ask for some input on topics that you all would like to have covered, and this popped up fairly high in the list. So we decided to come back and address it now, and then in the next couple months, we'll focus a little bit more on the Z13 specifically. So with that, let's go to slide 2. This slide has been around for a while. It was originally put together when the encryption facility first came out to document the capabilities there. So it goes back. The encryption facility was introduced, I want to say, back in 2005. When ZOS 1.6 was the standard, or was the current operating system. And historically, the encryption facility was actually available before that as a no charge download on TechDocs. Some IBMers had put together some programs that would do file encryption. It would encrypt sequential files. And what happened back in that early 2000 timeframe was there were several instances of tapes falling off of trucks and getting lost. And with the California Senate bill, if you lost data, you had to turn around and notify your customers that their data potentially had been lost, had potentially been compromised. So IBM customers started meeting on IBM for solutions to the problem. They started looking for file encryption capabilities so that they can encrypt those tapes before they went off site. And that way, if the tape got lost, they didn't have to go through the notification process. So IBM took this utility off of TechDocs, basically just beefed up the documentation and put a formal support structure around it, brought it into the formal support structure that IBM provides. And so now this utility was available as a program product called the IBM Encryption Facility for ZOS. The original version was 1.1. We're now up to 1.2. And basically, it is just a file encryption. It provides the ability to encrypt sequential files, and so that you can protect them, when they leave your control. The original version 1.1 supported what was called Z format data sets, and it's version 1.2 supports Z format as well. Z format is basically a proprietary format for creating the encrypted copy. It basically just sticks a header record on the beginning of the encrypted file with information about the file. And we'll touch on that a little bit more as we go along. Along with providing the program product, IBM also provided a couple of web downloads, no-cost utilities, so that you could share data with your partners even if they weren't licensed for the encryption facility. So there in the middle, you have the Java client. Basically, what the Java client gave you the capability was if you were licensed for the program product, the encryption facility, you could create an encrypted file and send it to your partner who might not be running ZOS, or even if they were running ZOS, they might not be licensed for the encryption facility product. They could read your file using this Java client. So it basically just ran in a Java environment, and it could encrypt or decrypt data. So they could encrypt data using the Java client, send it to you. You could read it, you could decrypt it with the encryption facility program product. So the licensing requirement for the Java client was that one of the parties, either the encryptor or the decryptor, had to be licensed for the encryption facility. But as long as one party was, the other one could use the Java client so they could communicate. There was also a decryption client. With that, your partner who was running ZOS but was not licensed for the encryption facility, they could install this web download. They could decrypt the files that you sent them, but they could not encrypt files and send them back to you. The nice thing about this was if they were running ZOS and they had crypto technology, they could take advantage of that crypto technology with the decryption client, but they weren't able to exploit the full product without purchasing the product. Um, Also, when the encryption facility was made available, in addition to that, the encryption services feature that just did straight encryption, there was also a DFSMS DSS feature. And what that did was it extended DFSMS DSS and gave you the ability, if you were using DSS to create your dumps, you could encrypt those dumps as they were created. So basically what would happen was you would run your DSS, whether you dumped the full physical volume or just logical volumes or just a group of data sets, it would create the DSS dump, but before writing it to the tape, it would encrypt the data, and it was the ciphertext that was put on the physical tape for going off site to your DR or your Iron Mountain. Um, so you had the ability there to create encrypted dumps as you perform the dumps. So there was you didn't have to go through and create the dump and then run it through the encryption services feature to encrypt it. And then when you wanted to recover the data, you would have had to have decrypted the data and then restored the dumps. This just made it all one smooth process. Basically, it just added some keywords to the DSS dump program so that you could invoke some of the same options that you can invoke with the encryption services feature. And we'll talk about those a lot more as we go along. Now, a couple years ago, OpenPGP started getting a lot more attention. Customers were looking for OpenPGP support, so the encryption facility was extended in version 1.2 to support OpenPGP. The original implementation, OpenPGP, was implemented at the RFC 2440 standard. I think in 2013, there was an APAR that came out that brought that up to RFC 4880, the current OpenPGP standards. One of the advantages with OpenPGP is that it is ZAP eligible. So if you have now ZAPs or ZIPs now, you can offload that work and save some CPU costs. And that can be a significant advantage, and we'll touch on that a little bit more as we go along as well. And then OpenPGP, the OpenPGP standard uses OpenPGP certificates. However, IBM and RACF work with X.509 certificates, so the OpenPGP support in the encryption facility can support either of those, and we'll touch on that a little bit more as we go along. The other thing to keep in mind is that the encryption facility can get expensive. It uses the encryption instructions that are available on the CPAC-F, or it uses the Crypto Express hardware to encrypt the data. And so you can chew up some general purpose MIPS when running the program. With the availability of encrypting tape drives today, that is a much more efficient, a much better solution for encrypting your tape data sets that need to go off site. So I think in the not too distant future, everybody's going to have encrypting tape drives. Right now, you still have to pay a little bit of a premium to get those, but I think, as new generations of tape drives come out, all tape drives are going to perform encryption, and that is a better solution for bulk encryption, for encrypting those dumps that need to go off site. The encryption facility still has a role. There are situations, there are cases where it absolutely makes sense to encrypt a file here or there that you need to share with a partner. Even if you're doing system SSL, if you're using FTP to send a data set to a partner, you can configure your environment so that that data gets encrypted as it's put on the link and sent to the partner. The problem with that solution is when the data gets put on the link, it's encrypted, and as it comes off the link, it gets decrypted. So when your partner receives it, System SSL, the FTP, is automatically decrypting the data. Now, if your partner is running some kind of a utility that basically just pulls file off of the FTP session and sticks them in temporary storage somewhere, that data may get stored in temporary storage that doesn't have the proper security, the proper protection for it. If they don't have their temporary data sets protected so that not just anybody can see them, then that data could potentially be compromised. If you use something like the encryption facility and encrypt the data before you send it to them via FTP, when it gets off the link on the other end, even if they've encrypted it as part of the SSL session, it's still going to be encrypted in that temporary file, and that partner is going to have to take another step, run the encryption facility on their end to decrypt the data, and hopefully at that point, they'll put it into a data set with the proper level of security and the proper levels of protection. So there is a usage for an encryption facility today. As you're sharing data with partners, it might make sense to take advantage of this. And if your partner is running in a OpenPGP environment, then you can use OpenPGP as well, but provide that additional protection so that they have to take an overt action to decrypt it and put it in the right environment and wrap the right security around it. So with that, let's go to slide 3. Before we get into the details of how the encryption facility works, I want to do a quick refresher on the hardware that's available. So if you remember, there's two types of hardware available on System Z. There's clear key hardware and there's secure key hardware. With clear key, your key material may exist at least briefly, at least for some short period of time, in the clear somewhere in your environment, whether it's in memory or whether it's in storage. With clear key technology, your key could show up in a dump. So in a minute, when we look at the options for generating keys, your key material may be generated by us via software, and it could show up in memory. Alternatively, secure key hardware, there's a secure tamper-resistant boundary, and your key material will never exist anywhere in the clear except inside that boundary. So if somebody tries to put a probe on the card and look at the electrons moving around, look at the key material, the card would detect that as an attack, and it would zeroize itself, wipe itself out before it would let your key material be seen by an outsider. Now, protected key was introduced a couple years ago. That's kind of a hybrid. It combines the speed of clear key with the security of secure key. Just be aware that the encryption facility does not support protected key technology. We're going to see in a couple minutes that the encryption facility does not use symmetric keys from the CKDS, from the key store. and therefore it can never or will never use protected key technology. And we'll get into that a little bit more as we go farther along. So let's go to slide 4 and look at the hardware. The ClearKey hardware on System Z is the CPAC-F, or CP Assist for Cryptographic Function. Think of that as just additional real estate on your general purpose engine. It provides some additional instructions that perform encryption operations. So there's instructions that do DES and triple DES and AES encryption, and there are instructions that perform hashing, the hash functions. So both of those are going to be used by Z format, the Z format OpenPG and OpenPGP implementation to perform the actual encryption. And then we'll see in a couple minutes that it's also used with generating symmetric keys that'll be used to encrypt the data. Let's go to slide 5. The Crypto Express cards are an additional feature that you've got to purchase separately. They provide that secure key technology, that tamper-resistant technology. They provide a number of functions listed here. The ones that are appropriate or applicable to the encryption facility are the secure key triple DES support. If you want to do secure key encryption of your file, you've got to have a Crypto Express 4S or on the Z13 now, a Crypto Express 5S to do that. But you've got to have that crypto card. In addition, it also supports RSA and ECC operations. So if you want to use, we're going to see in a minute that you can specify an RSA option. When you do, that implies that you've got a Crypto Express card available to service those operations. So let's go to slide 6. Let's look now at how the encryption facility works internally in terms of how it protects your files. Uh, there's two options that you have to worry about specifying. One of them has to do with whether you're going to use clear key or secure key technology when you protect the file itself. But before that, you've got to specify and tell the encryption facility where the key material is coming from. And there's two ways to do that. There's a password option and there's an RSA option. So for the password option, you're going to provide a password or a passphrase as input to the utility. The encryption facility is going to take that string and using a PKCS12 implementation, it's basically going to take that string and run it through a hash algorithm and generate a unique bit string that represents the hash. And then the bits and bytes are going to be pulled out of there to be your symmetric key. So the file itself is going to be encrypted using a symmetric algorithm and a symmetric key, and the key in this case is generated from that password. So you're not going to put the password in the file. You're not going to stick the password on the outside of the tape that you're going to send to your partner or send off site. What you're going to have to do is provide that password via another channel, another path. So you'll pick up the phone and call them and say, hey, the file I'm sending you today was encrypted with the passphrase of Tippecanoe and Tyler 2. Or maybe you're going to put it in an email and say, all right, all of the files that I send to you this week are going to be encrypted using the password Tippecanoe and Tyler 2. Your partner, when it comes time to decrypt the data, they're going to provide that same password, that same string as input. It'll get run through the same algorithm to generate the same hash value. The same bits and bytes are going to be pulled out to be your symmetric key. And then that's going to be used to actually decrypt the data that's in the file. Now, IBM does caution when you're using the password to stick to upper and lower case and standard numerics on the keyboard. Otherwise, if you're communicating with somebody running a Java client, you might have to worry about code page issues. But uppercase and lowercase and numerics are pretty straightforward. You don't have to worry about it as much. But the password option is fairly simple. You are providing a string that's used to generate the key material. Let's contrast that with the RSA option on slide 7. The RSA option works a little bit differently in that the symmetric key that is used to actually encrypt the file, encrypt the data, is simply a random number that you generated every time you run the utility. So you'll get a different random number every time you run the utility. That will be used to encrypt the data. In addition, that symmetric key is itself going to be encrypted using a public-private key pair, and the encrypted copy of the symmetric key is going to be stored in the header record of the encryption facility file that's created, the ciphertext file. So what that means is when you're going to encrypt data for a partner, before you can perform the operation, before you run the utility, you've got to get your partner's public key. Maybe they're going to send it to you via certificate, but you're going to import that key into your environment, put that key material into the ICSF PKDS, and then when you run the encryption facility, you're going to point at your partner's public key and tell the encryption facility when you generate that random number, encrypt it so that he'll be able to decrypt the symmetric key. So now you don't have to communicate with your partner each time you send them a file and tell them what the passphrase is. When they decrypt your file, they're simply going to point to their private key that corresponds to the public key that they sent you. The encryption facility will pull the encrypted copy of the symmetric key out of the header record, decrypt it using their private key, and now they have the symmetric key, the random number that you generated. They can now decrypt the file itself and recover the file and use it going forward. Now, if you're creating an encrypted copy for your own purposes, for DR, for archive, whatever, you're going to simply point to the public-private key pair that you've generated in your environment. If you're sending it to a partner, then you're going to have their public key installed. Now, in addition, the encryption facility will actually support being able to specify two different public keys. And the idea here is if you're creating a file for your partner, you might want to validate that you've got that what you're sending them is good data that they're going to be able to recover. So what you can do when you encrypt your file, you can point to your partner's public key. You can also point to a public key that belongs to you. And that symmetric key will get encrypted twice, once under your partner's public key, once under your public key, and both of those will be stored in the header record of the file. Now, once the file is encrypted, before you put it on a truck and send it to them, you could turn around and test it and try decrypting the file, pointing to your private key that corresponds with your public key. If you can decrypt the file using that, you know that your partner should also be able to decrypt it on the other end, but using their their private key with the cipher, the copy of the symmetric key that's encrypted and stored in the header record. So there is support for two different public keys being able to be stored in the header record. So with that, let's go to slide 8. The hardware that you require is dependent on which of those two options that you specify. So if you choose the password option, you're going to provide an 8 to 32 byte password that's going to be run through that PKCS12 algorithm that's going to rely on hashing to generate the key material. All of that work is done on the general purpose engines, the general purpose CPs. Now, you might use the hash instructions that are part of the CPACF, but again, think of that as just additional real estate on the general purpose engines. So if you choose the password option, that's going to use up some MIPS, and you don't have to have a Crypto Express card when you specify the password option. Alternatively, if you want to use the RSA option, remember when we talked about the hardware that the CPAC-F does nothing to support RSA encryption. You've got to have a Crypto Express card if you want hardware support for those operations. So you have to have a Crypto Express card installed. If it's configured as a coprocessor, you've got to have the master keys loaded to enable that RSA support that's available on the Crypto Express card. Let's go to slide 9. Once you've told the encryption facility where the key material is going to come from, whether you specify the password option or the RSA option, you then have another choice to make in terms of how and where you want the actual encryption work to be performed. So you've got a couple options. You've got clear AES, you've got clear TDES, and you've got encrypted TDES. If you specify clear AES, what you're telling the encryption facility to do is to use an AES 128-bit key on the clear key technology using the symmetric algorithm running on the CPAC-F hardware. It's going to be performed with AES 128-bit encryption. Now, on the really old machines, the 890s and 990s, the 800s and 900s, those machines did not support AES encryption at all. However, ICSF did support AES encryption in software. Now, the performance might not be the greatest, but the work would still get done on those machines. Notice also that there's no support for AES 192 or 256-bit keys. The encryption facility was developed when the Z9 was the current technology, and the Z9 only supported AES 128-bit keys. It did not support 192 or 256-bit keys. So the encryption facility does not support 192 or 256-bit keys. Alternatively, you could specify clear TDES as the option, and that tells the encryption facility to use triple DES encryption. At the time that the encryption facility was developed, the writing was on the wall that DES was not a good solution anymore and you should be moving away from it. So the encryption facility does not support single DES encryption at all. It only supports triple DES. On all of the Z890s, Z990s and forward, that's supported in the CPAC-F hardware. That clear triple DES is done in those instructions. On the Z800 and the Z900, the CCF supported triple DES encryption. Now that was a secure key technology, but the encryption facility was smart enough to say, well, you know what, we're going to even give you a little bit extra security, but we're going to do it in the hardware just because the performance is so good on that hardware. And you really don't even realize that we're using secure key hardware on those machines. The third option is encrypted TDES. That's telling the encryption facility to use secure key triple DES encryption. Again, doesn't support single DES with secure key. On the various platforms, you have to have the appropriate crypto card installed. So on the ZEC12, that would be the Crypto Express 4S or the Crypto Express 3. Going back to the Z800, that would also be performed on the CCF hardware as well. Now, I want to point out here that there is no support for AES secure key. Again, when the encryption facility was originally rolled out, when it was developed, there was no support for AES secure key. So the encryption facility does not support AES secure key. And given, as we've already mentioned, that tape encryption is probably a better solution for bulk data encryption, not sure that I would expect to see any enhancements coming to the encryption facility to support secure key. But if you need it, then it would be appropriate to open a requirement with IBM to see if you can get that added. Let's go to slide 10. So let's talk about compression for a little bit. Whether you realize it or not, for a number of years, tape drives have done compression on your behalf. When you write data to a tape drive, the tape drive is going to perform or try to perform compression for you and save some space on the tape. So repeating spaces or repeating data is going to get compressed down, and it makes more efficient use of the space available on a tape drive. The problem you run into is if you encrypt data before you send it to the tape drive, you've taken all of those repeating blanks and repeating data and turned it into random bits and bytes, and suddenly compression no longer works. If you encrypt the data first, as you write it to the tape drive is not going to be able to compress that data. So, what was happening, or what could have happened, was if you were, say, using DFS and SDSS to dump your data, and the tape drive was finding all of these spaces and compressing them, if you encrypted it, now that data is not going to get compressed, and potentially a dump that used one tape today would, if you started encrypting the data first, it could use two or three tapes instead. So the number of tape draw or the number of tape volumes you need could potentially go up fairly significantly for a large shop. So the encryption facility gives you the ability to encrypt or to compress the data before you encrypt it. Now, the tape drives are very, very efficient, and that work is done in the tape drive. If the compression is done in the tape drive. However, if you specify the compress option to the encryption facility is going to use general purpose instructions on your CP to perform that encryption. So it's going to compete with other work in this system. It's going to use up more CPU MIPS to compress that data. But you do have the option. You can tell the encryption facility, compress the data first. Let's save the tape drives that we're going to need at the expense of driving up the CPU utilization and using a lot more CPU MIPS. So that's another option that you can specify as you perform the encryption to tell it whether you want to compress or not to compress as you create or before you encrypt the data that's going to get put into the file. Let's go to slide 11. There's a couple other parameters that are of interest. There's a description parameter so that as you create an encrypted file, you can put some free-form text in here and that will get stored in that header record. So you might put some description of what the data is that's in this ciphertext that you're creating. So if you come back and look at this file a year from now, you can't read the ciphertext, but the description might tell you, oh, this was the encrypted copy of such and such a file, such and such a customer file, maybe on this date or whatever. The iCount parameter has to do with the hashing of the passphrase. So by default, the algorithm says that they're going to run 16 iterations of this hashing operation to come up with a hash value that represents the passphrase. You could specify a much higher iCount, which will give you better security. And if you look at what's going on today in the recent announcements for RACF protecting the password in the RACF database, the issue there is you can do what's called a brute force attack. You can run a hash operation and come up with a dictionary of hash values. But if you perform more iterations, that makes it much more expensive for an attacker to come up with a dictionary. They've got to run more iterations to build the dictionary. So by increasing your I count, you can make the security around your passphrase even stronger if you think that's appropriate. And then the last option there is the info option. That's only available for reading a ciphertext file. It's only available or it's only supported for the decrypt operation. And basically what info does is it will pull information out of that header record that's at the beginning of the file to tell you things about the file itself. So there's some of the information that's in that header record is the DCB of the original file. The description in the descript parameter is stored in there. The info will display that description for you, so if you need to look at it. Let's go to slide 12. Now, I hesitate putting this chart in here because it's really old. Way back when the encryption facility was first published, there was a tech docs that was available that provided some performance information. That tech doc is no longer available, although I do reference it at the end of the slides. But what happened was IBM put together some kind of benchmarks so you could get an idea of what it would cost you for the various techniques. So what this chart is saying, and we'll focus on the Z9 because that's as close as we can get to the current performance. If you were running on a Z9 and you specified clear TDES, you could expect to encrypt about 143 megabytes per CPU second. All right. Now, if you added the compress option and compressed the data before you encrypted it, um, your throughput dropped to about 64 megabytes per CPU second. So what this is saying was if you had a 143 megabyte file, it would take you about a CPU second to encrypt it using your encryption facility and clear TDES. If you turn on compression, it would take you a little bit over 2 CPU seconds to encrypt that file. So you could, look at the amount of data. If you were doing dumps and you had X gig of file, you could calculate roughly how many CPU seconds it would take you. If you wanted to do clear key AES, you could do about 167 megabytes per CPU second. But if you turned on compression, then it would drop to a little bit less than half of the throughput. Secure TDES, that work has to get routed out to the PCI card to get done. Your throughput drops pretty significantly. You could only do about 52 megabytes per second with secure TDES, and if you turn the compression on, it dropped to 42 megabytes. So again, the other point I want to emphasize here is 143 megabytes might take 2 CPU seconds with the encryption facility. If you use encrypting tape technology, all of that work's done in the controller. It's not going to show up as CPU busy. So once again, tape encryption is a better solution for encrypting bulk data that needs to go to tape. The encryption facility still has a place in sharing data with your partners, but for bulk offsite tape encryption, look harder at the tape technology. We do have a couple customers that are still using the encryption facility to encrypt their dumps as they go off-site, but these are kind of special case customers, I think. I know of one that they don't do any processing on the weekend. They don't have any work running on the weekend. So on the weekends, they've automated their dumps. They'll run their dumps and create the tapes and use that idle machine to perform the dumps on the weekend. But unless you're a special case like that, you got plenty of available resources. You probably need to be looking at tape encryption for bulk data encryption and bulk protecting bulk data before it goes off site. Let's go to slide 13. So this slide is kind of comparing some of the options that you have available to, specifically related to Z format and whether the partner that you're exchanging data with has the encryption facility installed or maybe wants to use one of the optional, the decryption client for ZOS or the Java-based client. So if both of you have System Z, ZOS, and the product installed, you've got all of the capability. You can do full function encryption and decryption. You got all the options available. You can do compression and decompression, and both of you can take full advantage of the hardware that you have installed. Now, if one of you has only the decryption client for ZOS, remember we talked about that back on the second slide. That's basically the file decrypt utility that's available as a web download. So one person can encrypt data using the encryption facility for ZOS. The other one can decrypt those files, but that other party can't encrypt in that case. When they are doing decompression, they can take advantage of the acceleration, or I'm sorry, not decompression. When they're doing decryption, they can also decompress the files if needed, if you had compressed them, and you can also take full advantage of the hardware that's available. When you get to the Java client, you can encrypt and decrypt in both directions, but the Java client did not support compression, so neither of you won't be able to compress the data, and you may not be able to take full advantage of the hardware. Depends on the Java implementation that you've got. So again, that's available to you if you're exchanging data with a partner that has or is not running ZOS. Then the OpenPGP is probably a little bit better solution at this point. And let's go to slide 14 and start talking about that a little bit. Oops, I got a little bit ahead of myself. One more slide before we go to OpenPGP. Just kind of wrapping up some thoughts with the Z format of the encryption facility. Um, if you want to use secure key, if you want to use that encrypt TDES option, or if you want to use RSA option, then you need that coprocessor available so you can have keys, the public-private keys in the PKDS, so you can perform the secure key encryption inside that secure key hardware. So you've got to have the coprocessors if you want to use either of those two options. In all cases, ICSF is going to have to be up and running. The encryption facility relies on the APIs, so the ICSF is going to be have to be active, even if you are using only ClearKey. You still got to have ICSF up and running and to get those APIs, get access to the APIs. Didn't really touch on it, and I probably should have. Uh, when you encrypt the file, the encryption facility will decide the appropriate DCB information for the output file. And typically it's going to use half tracks, or if you're writing to disk, or it's going to use 64 or 32K if you're writing to tape in terms of the block size. You don't have any choice over that. Now, when you perform the encrypt, the original input file, the DCB of the original input file, is captured and is stored in the header record. So when the decrypt is done, it'll go look at that, and by default, it'll allocate the new clear text file with the same DCB as the original. You can override the block size, but you can't override the LREC. So with that, let's turn and look a little bit more closely at OpenPGP support. So OpenPGP is now a formal internet standard. 40, as we described earlier, RFC 4880 is the current standard. It's a standard for encrypting files and packaging those files for delivery for sharing with a partner. Now, just like the Z format, you can use either passphrase or public-private keys to provide some security. There's a subtle difference there, and we'll get into that in the next slide. Um, the OpenPGP standard supports compression of data. So if you've got some large files and you want to save space, then you can do that as well. The standard describes the use of OpenPGP certificates. So these are certificates that are unique to OpenPGP, but the encryption facility also has support for X.509 certificates. So what that means is you can use RACF as your key store. So as you get these X.509 certificates, you can store them in RACF, and that can be your key store. Or you can use ICSF as your key store, and RACF and ICSF can work together, with RACF protecting and storing the certificate information while ICSF holds the key material. And then thirdly, you could use just a traditional Java key store and store the certificates in there as well. OpenPGP does give you the ability to create one file that can be shared with multiple partners. So where the encryption facility only supported 2 partners, you can support a variable number of partners with OpenPGP. And again, the idea is you could create one encrypted copy of a file, and then the symmetric key that encrypts that file would itself be encrypted, and multiple versions of that ciphertext would be stored in the OpenPGP file. So you could then distribute it to 10, 20, whatever different partners. Each one of them will be able to pull off their version, their ciphertext copy of the key, and decrypt it using their private key. And then lastly there, the OpenPGP does provide some advantages in terms of text processing. So with OpenPGP, you don't have to worry about the EBCDIC ASCII conversion. That's kind of built into the standard. So there's an advantage there as well. Let's go to slide 16. So OpenCryption or OpenPGP does provide both support for both passphrase and certificates, just like Z format. But the subtle difference is that no matter which one you choose, your data is always going to be protected by a random number. So with the OpenPGP, what happens is the OpenPGP implementation will generate a random number. It'll use the hardware or whatever facilities are available to generate a random number. That's what's going to encrypt your data and protect your data. And then that key, if you choose the certificate option, just like with Z format, that key will be encrypted with the public key of a public-private key pair and stored in the structure in the OpenPGP file that's created. If you choose the passphrase option, just like with Z format, the passphrase is going to be hashed and a key is going to be generated. But with OpenPGP, that key is going to then encrypt the data key. And again, it'll be stored in the structure in the file that's created. So they work very similarly, just a subtle difference there that in both cases with OpenPGP, the file itself is encrypted by the symmetric algorithm using the random number that was generated. Let's go to slide 17. The OpenPGP support within the Encryption Facility product is implemented as a Java application. So that means you can run it from your OMVS environment, or you can invoke it. You can invoke OMVS support using batch. So you can build JCL and batch jobs that will invoke it and perform the operations for you. Now, because it's Java, that means that in your Java configuration, you can configure things and you can define like the crypto environment that you're running in. So you can define and say that your crypto provider is going to be software. And that's it. That tells the Java environment, hey, I don't have any hardware. Just use Java routines, Java encryption routines to generate the random numbers, generate the key material, perform the encryption operations that need to be performed. Alternatively, if you have the hardware installed and it's available in your ZOS environment, you can specify that Java has crypto hardware providers available, in which case the encryption facility will call the appropriate routines and Java will call the appropriate hardware to perform the encryption operations for you. So when you need clear key encryption, it's going to route that work to the CPAC-F hardware. When you need RSA operations, it's going to route that work to the Crypto Express card if available. So there's a configuration file that you have to set up and configure and tell it what kind of environment. If you've got the hardware, you want to make sure that you specify a crypto provider that will go to the hardware. And if you don't have the hardware, then you want to make sure that you specify a crypto provider that tells Java to go ahead and do the work in software. The work will get done. Performance may or may not be acceptable, but at least the work will still get done. Let's go to slide 18. Um, the encryption facility, the OpenPGP support can get data out of a ZFS, or it can use the typical Z format or Z data sets, PDSs, PDSEs, sequential data sets. You just will point to those in the JCL or in the input to the Java control statements that you provide. Now, The OpenPGP support will look for a OpenPGP keyring. That's where the certificates are going to be stored. So you have to create that key store within your OMBS environment. Point to that as part of your configuration for the OpenPGP environment. On slide So IBM introduced this APAR OA 40664 in January of 2013 to bring the OpenPGP implementation up to the 4880 standard. Prior to that, 4880 had been out for a while. A number of other vendors had implemented it. And what was happening was a partner was creating a file using that 4880 implementation on another platform, sending that to an IBM system, and the IBM system was having problems recovering the data because there was additional information in there with the 4880 that it didn't know how to handle and it wasn't compatible. So IBM had to bring this APAR out. Now, in addition, they provided some new security capabilities in the speculative key ID support there. What that means is that uh, prior to this, you stored information about the public key that was used to encrypt the symmetric key in the package, in the file. With this support, that information is no longer there, which means the receiving system that's going to have to decrypt the data has to figure out what the right public key was to decrypt the symmetric key. And there's techniques for doing that. There's ways to do that. By doing that, that provides a little bit more security. You don't have any information in the file about the public key that was used to encrypt it. So there's some more work that has to be done on the receiving end, but it provides better security. That third bullet there, the support for notation data subpackets. Um, with RFC 2440, you could create notes and put information into the package that would be stored there and transmitted with it. But it was done with a UTF-8 format, so it was human readable. With this support, that information can now be stored in binary instead of in a human readable format, so it's a little bit more efficient. Let's go to slide 20. So as we mentioned earlier, the OpenPGP model relies on a different certificate structure than the X.509. OpenPGP relies by default on what it calls a web of trust model. And the idea is that multiple people can sign or vouch for a person or a person's certificate. So, for example, Alice may know Bob. She may have a copy of Bob's certificate and know that it's Bob's certificate because she's met Bob and she trusts Bob and she knows this is his certificate, so she can sign his certificate. You know Alice and you trust Alice, so by virtue of the fact that she signed Bob's certificate, now you can trust that you have Bob's public key via his certificate as well. And in that web of trust model, multiple people can sign a certificate. So maybe not just Alice, but Fred, George, and John also sign Bob's certificate. And you know Alice and Fred and George, so you even have more trust, more confidence that you have Bob's public key via his certificate. So that's the web of trust model. However, within OpenPGP, it can also work like the X.509 model in that you can install a CA, a certificate authority, and that root certificate, and then any certificates that it has signed and that it vouches for, you can trust those as well within the OpenPGP model. So within the encryption facility, it does not support that web of trust model, but it does support OpenPGP certificates when the environment is configured like that X.509 model. So that can provide you some flexibility and you can go either way in terms of the certificate to support that you need. And you can define those certificates via RACF. You can use the RACDcert command, and we'll see a little bit more about that in a minute, to install and manage those certificates. So let's go to slide 21. And here we see that RACF does provide the rack dsert command for managing digital certificates. You typically would use the gensert, the export, and the add command. The gensert to create a new certificate, the export when you need to export a certificate to your partner, and an add to bring a certificate into RackF from your partner. Now, there's some keyword options, specifically the PCI-CC down there. That tells RackF, you manage the certificate information, but take that key material instead of keeping it in the RackF database, move that into the ICSF environment, or move that into the ICSF key store into the PKDS, and then that way you provide the most security for the key material, but the most flexibility in that you can manage the certificate from the RackF environment. And again, as we mentioned earlier, you can configure your OpenPGP environment so that it knows just to use RackF, or that it knows to use RackF and ICSF, or possibly that just to use ICSF as the key store and not even mess with RackF. So you got a couple different ways you can manage that key material within the OpenPGP environment. And since RackF supports X.509, you can also manage the keys for a Z format environment as well. Let's go to slide 22. I'm going to take a quick brief detour here. I should have mentioned on the last panel that you don't have to use RackF to manage your certificates. You could use ACF2 or Top Secret as well. You just have to use the appropriate commands for each of those products. But you don't have to use your security product at all. ICSF does provide the ability to create and manage PKA keys in the PKDS directly from the panels. You just go to the ICSF Utilities panel, which we see here, and then select option 6 for managing the keys in the PKDS. That'll take you to slide 23. And on this panel, up at the top, you provide the label for the public-private key pair that you want to manage or take care of in the PKDS. And then you have 4 options. You can generate a new key pair, both the public and the private key, and you can tell it what links to use. You can delete a key that maybe has already been defined. You can export that key so you can get the public key out in a certificate such that you could send it to a partner. And then finally, that last option down there, you could create a key in your PKDS from a certificate that your partner has provided to you. So you can import that public key into your PKDS. So you can manage these certificates in X.509 format from the ICSF panels. So with that, let's go back to the OpenPGP discussion on slide 24 and start wrapping things up. Now, it's important you realize, and I think you probably already picked up on this already, that OpenPGP format and System-Z format are very different. They're not interoperable. You can't generate a file in System-Z format and have your partner read that file using his OpenPGP implementation. It's just not going to work. Then the other point on this chart is that the OpenPGP implementation has changed over time. Part of that is, just the change in standards from 2440 to 4880. OpenPGP has gotten more sophisticated, more flags, more bells and whistles. So there are different levels. There's a version 3 and a version 4 type of certificates. There are version 3 and version 4 signatures. The version 4 are just a little bit more sophisticated, a little bit more expandable than the older versions. The OpenPGP implementation with the encryption facility can handle either of those versions as input. However, if you create a certificate today, it's going to create it using the version 4 format just because that's the most current. So similarly, if you create a signature, it's going to create a version 4 signature as opposed to a version 3 signature. So you can handle both, but going forward, you're going to output just the version 4 levels. So with that, let's go to slide 25. So wrapping things up here, this slide contrasts Z format with OpenPGP format. So first of all, Z format can only handle ZOS datasets. So whether it's sequential files or PDSs or PDSEs, that's what Z format will support. It can't access files in the Z file system. OpenPGP, on the other hand, running in the OMVS environment, can access those files in the Z file system, and it can also access the ZOS data sets. You can point to those outside of OMVS. Now, um, the next point on there is the fact that you're going to get much better performance out of Z format. That work is going to be routed through ICSF directly to the cards, and you're going to get the best performance out of your CPAC-F and your Crypto Express cards. In the Java environment, the Java implementation, you do have the flexibility that you can configure a software provider, so you don't have to have the Crypto Express cards, in which case the work's going to get done by software routines and the performance is really going to drop off. Or you can configure the crypto hardware provider, and Java will route work through the provider to ICSF and then to the hardware. So you can use the CPAC-F or the Crypto Express card, but you've got that additional overhead of going through the Java environment. Now, offsetting that to some extent is the fact that the work can get offloaded because it's Java. It can get offloaded to zips or zaps, and so you can save some CPU, some MIPS by routing by running the work on the zips or zaps. And then down at the bottom, note that no matter which one you're using, both of them can rely on the key management that's available with ICSF, the security and the integrity of the public-private keys that are stored in your PKDS. So let's go to slide 26. The encryption facility can support one of three algorithms. It can support AES with clear key. It can support triple DES either with clear key or secure key. And it can support the Blowfish algorithm. Now, Blowfish is only supported when you're using the OpenPGP format. That's one of the algorithms that OpenPGP has specified. Now, the encryption hardware does not support Blowfish, so if you specify Blowfish, that's going to be done in software routines with some performance penalty because of the overhead of doing it in software. Now, when you start making choices as to whether you want to use passphrases or RSA keys, that might drive some of your hardware requirements. The passphrase, if you specify passphrase, that work's going to get done on the CPAC-F hardware. If you specify the RSA option, then the encryption facility expects you to have the Crypto Express cards available because that's where the where the RSA work is done on those secure key devices. Now, if you use OpenPGP, you don't have to have a Crypto Express card, but again, the performance could be a little bit better if it's available because that hardware does provide much better performance for PKA operations. So let's go to our bibliography on slide 27. At the top here, you have the encryption facility publications that come with the product. In the middle there are some red books. That third red book was specific to the first version, version 1.1 of the encryption facility, so it's specific to Z format. The top two there are more focused on the OpenPGP implementation. And then at the bottom, I did reference a couple of the tech docs that are no longer available. I think IBM let them expire when shortly after I left last year. If you have access to them, there is some useful information in there in terms of how Z format works, but those were written before OpenPGP support. Those were also written when the Z9 was the current technology, so any of the performance information in there is kind of dated and is specific to the Z9. They haven't been updated for the later machines. So with that, we'll flip over to slide 28. And I'll land here only long enough to say thank you for sticking with me. And we'll turn things back over to Jerry and let him open the session up for questions. Jerry?